Hello, lesson 2, electric fields. So yesterday we looked at Coulomb's law, so the force between charges. What we're interested in today is the area around a charge where forces can occur, and we call that an electric field, very similar to a magnetic field being the area around a magnet, where magnetic force can be felt, electric field, an area where electric force can be felt. Now, the direction, we have to understand the direction. The direction of electric field is where a test plus charge would go. So effectively, if you put a plus charge beside a plus charge, it's repelled, and if you put a plus charge near a minus charge, it's attracted. So effectively, electric field lines go from plus to minus because that's the path that a plus charge would take. We'll just look at a few examples. Okay, if we take the simplest scenario, so a plus charge, the electric field will be away from the plus charge. Okay, and we call it a radial electric field. Minus charge, it'll be towards, okay, in exactly the same way, but towards. And if we just take one example of a plus and a minus close to each other like this, well, the plus will go away and it'll be attracted into the minus. So it's going away, attracted to the minus, going away, attracted to the minus, and so on. And you will notice that the field, there's huge links between electricity and magnetism. Okay, and you can see that the field here looks very like an electric field. Okay, or very like a magnetic field. It is an electric field. So that's the direction. Okay, so you put a plus charge in and you see where it goes, and you understand the idea that an electric field is where electric force is felt. Next thing we want to look at is the size of the force. Okay, which effectively is how big the electric field is. Okay, and we take the same attitude as we've done before, in that we take we're going to put a charge into the field and see what force it experiences. And the obvious thing is take the unit charge. Okay, so we always take units. So remember, we take per meter squared, and so on earlier on in mechanics. So here we're going to use per coulomb. Okay, so the electric field strength is going to be the force per coulomb, and we can write it like that: force per coulomb, or Q. And I'm using small q here for a reason. Q is the test charge you've put in. Okay, so it's E is F over Q, force per coulomb. If you think about it, if the force is 20 newtons and it was 4 coulombs, well, then it'll be 5 newtons per coulomb. So F divided by Q. So that's where that's coming from. So that's the definition. The unit we use, okay, force is newtons divided by coulombs, so newtons per coulomb. So nothing complicated there. Pretty straightforward. Okay. Next thing we want to look at, though, is the issue that, okay, if we have a plus charge here, okay, and if I want to find the electric field strength at a distance d from this charge q, okay, this formula is not good to us because we don't have F, we don't have the test charge. We have the charge causing the field, and I'm going to call the charge causing the field uppercase Q, and the test charge thrown into the field lowercase q, big Q, small q. Okay, that's not in the tables. We're going to think it like that as we go along. Okay, so let's take this and let's see what can we get anywhere. Okay, can we get a more appropriate formula? And we can, using Coulomb's law. So we're going to write down Coulomb's law for this. 1 over 4 pi epsilon Q, the test charge here, small q over d squared. Okay, now think about it. If it's the electric field strength, the test charge is 1. So we're going to do that. We're going to change the force to electric field strength. But if we do this, we have to change that to 1. So the formula becomes E instead of Q, instead of F, and the test charge is gone because Q times 1 is the same as, or uppercase Q times 1 is the same as uppercase Q. And that's it. No, big exclamation mark on that, because that's not in the tables. It's really, and it's kind of amalgamating the two of these, but I think this is the easiest way of looking at it. You're using Coulomb's law. If you're changing Coulomb's law into an electric field strength formula, the F becomes an E, and the test charge, small q, goes. Okay, because instead of capital Q by small q, it's not just capital Q by 1, which is capital Q. And that's it. Okay, so that's okay. One last thing. If you're doing calculations, all right. Okay, and if the charge has dimensions, in other words, if it's a sphere or something like that, rather than